Welcome to a quick guide on IR spectroscopy. Over here I have graph. On my x-axis I have wavelengths of visible light. So I have purple, blue, green, RGB. And on the y-axis I have their intensities. So let's say if I have a lamp which is shining white light. So on the graph I'll end up seeing a straight horizontal line. Why? Is because all of these colors are in equal intensity and they mix up together to form white light that's coming out of this lamp. Let's say now I have a blueberry and the lamp is shining equal light onto it. When I say equal, I mean they're all of equal intensities. White light, so all of these colors are at equal intensities. So the berry looks blue to the eye, right? This is because most of the light is absorbed into the berry and some of the light is reflected back right into the eye. So if I see it as purple right now, that means most of the purple light got reflected back. So if I ended up drawing its diagram, so this is the light that was reflected back. So all of purple came out, but very little of blue and green, yellow, and red were nowhere to be seen. So all of these colors combined end up looking like this shade of purple in the eye. Let's say now I had something of a different shade. Let's go with an apple. Again, I shine white light onto it, and some of the light is reflected back, most of it is absorbed. Now, if this was for the blueberry, number one, the curve number one, for the apple, it's going to look something like this. So it's absorbing most of the color spectrum here, but it's leaving out red mostly. So this is what it's going to look like. Maybe a bit steeper early on. Okay, something like this. This region would be reflected back and I end up seeing red. Let's see now how this applies to a IR spectroscopy curve. So here's a very scary looking graph. Let's try to see what it means. So over here I have an organic molecule and I shine infrared onto it. Now these bonds can absorb different shades or different frequencies or different wavelengths of this infrared. The infrared is spread out over this range, and some of the bonds, these particular bonds, can end up absorbing different little regions. So over here, a particular bond in this molecule has ended up absorbing this range of light, this range of infrared. And whatever is reflected back from this molecule is picked up by a sensor, which ends up plotting this graph. So over here, we can see some regions, the molecule has absorbed certain bits of infrared light. So using this data, we can figure out, and referring to a data sheet or a data booklet, we can figure out what type of molecule this is, especially what type of bonds does it have, or what type of functional group does it have. So let's try figuring that out, how that works. Certain bond types and their range, their frequency range in which they absorb is mentioned. So the carbon-oxygen bond will absorb between 1040 to 1300 range. A carbon-oxygen double bond will absorb from 1640 to 1750, this entire range, but depends if the carbon-oxygen bond is right next to or is a part of an amide linkage or is a carbonyl compound or an ester, so it'll have different ranges. So we don't really end up worrying about this too much. We get a much general idea by just looking at the graph, but even though these are like a lot of information to take into absorb in one go. So the key parts are this region, the OH bond, and this part. So amides aren't exactly in the syllabus of A1, so we don't have to worry about it too much. And for the OH, it's a very characteristic curve which we end up getting, so it's very easy to recognize rather than looking at the values. I'll tell you what I mean in a bit, but let's take a look at this column right here. So over here, S means for strong peak and W means for weak peak. So over here, this peak, very obvious, and these peaks are considered strong peaks. Strong peaks, right? And a weak peak would be this part over here, this little peak over here. This part, that would be a weak peak. Now here, we're taking a closer look at an infrared spectrum of a molecule. Now, one thing to note is that any value lower than 150 over here is considered in the fingerprint region. Now the fingerprint region is 99% of the time, or like, let's just go all the way, not really our concern. So we'll just remove all of this crap from what we're trying to absorb. So we're left with this very unique peak on the left hand side and this very sharp peak. Now this would be a sharp broad peak because how big it is, how wide it is, and this is just a sharp peak. Now over here it's telling you it's a carbon oxygen double bond peak, and over here this OH, this is a OH peak, but the style of it is telling you that it's a carboxylic acid. So very likely this entire molecule is a carboxylic acid. Moving on. Now when you have a hydrocarbon, that sort of bonds you'll end up seeing, especially in the infrared spectrum questions, is the CH bond. And this is going to be the most obvious one. It's a hydrocarbon. You will have CH bonds, and you will also have carbon-carbon bonds. So you really don't need to look for these. It's obvious they'll be there. So the important ones are going to be the carbon-oxygen bond, the carbon-carbon double bond, if it's an alkene, the carbon-oxygen single bond, which highlights that it's an acid or an alcohol, and the OH bond. Of these, the OH bond is going to be the easiest to see, just because how wide it is. Now the OH bond can show up in two cases, when you either have a carboxylic acid with an OH bond right here, or you could have it as an alcohol. What kind of alcohol, primary, secondary, tertiary, doesn't matter as long as it's an alcohol. Now for the case of an acid, you'll have a very characteristic broad peak, and so for the alcohol. They're both broad, they're both strong peaks. But if you look at them closely, they're very different from each other. So this almost comes in two loops. They look like two different peaks even though they're the same peak. And for the alcohol, you see how smoother it is, how rounder or how lobe-like it is as compared to the one for the acid. So this reminds me of like an upside down iceberg. So in my head, I'm always thinking, oh, it's an iceberg peak. And that belongs specifically to a carboxylic acid. Not just ethanoic acid, it's specifically for a carboxylic acid. It's ethanoic acid because this belongs to a 2-carbon molecule, so we can deduce it's ethanoic. Over here, This is ethanol with just this characteristic lobe-like peak. And it's called a peak. It's definitely a dip, but it's called a peak anyway. Don't let the word confuse you too much. Another thing to note is that the ethanoic acid has a characteristic carbon-carbon double bond peak as well. So if you have a peak, if you have this peak present, let's say in a molecule, and this isn't there, so you're very sure you're dealing with a carbonyl compound or even an ester. Notice how there's no carbon-oxygen double bond peak here because ethanol doesn't have any, so that peak won't be present here. Now, you don't really have to remember the peak range for this and the absence of a peak over here, I guess. But you don't have to remember it because it's all in the data booklet. All of these are there. But just to make your life much easier, just by looking at this graph, you can tell which one of them is an acid and which one of them is an alcohol just by the shape, not the range, just by the shape of it. This is characteristic for an alcohol. So you'll get something similar. So it might vary a lot, but if it's very smooth and round, definitely alcohol 99% of the time. And this iceberg shape, definitely. So it might come out as a bit softer, something like this. And this could be a little sharper, but it'll be very unique between the two, right? So this will make your life a lot easier once you figure this out. Moving on. So here's a question. I have 3 graphs for 3 different molecules, and I have 3 names of 3 different molecules. Now I have to figure out which of these 3 graphs belong to which of these 3 molecules. Now before I start anything, I can see my characteristic iceberg right here. Very unique, very different from my lobe. That lobe shape comes back. I call it a lobe because it looks like the lower part of a ear. That's a earlobe. Anyway. And in the third one, I have nothing. I don't have anything characteristic, right? So what options do I have? On the left, I have ethanol, ethanoic acid, and ethyl ethanoate. Now, ethanol will have my OH bond, but it'll have the lobe. So this is my ethanol. For ethanoic acid, it'll have that characteristic iceberg shape because the OH, again, this belongs to these two are for the same bond, the OH bond. The only difference between the two is the OH for an alcohol will be a lot smoother, lobe-like, and the OH for the acid would be a lot like a flipped over iceberg. Now, ethyl ethanoate won't have a broad, sharp peak in this region is because it doesn't have an OH bond. There's no OH bond for ethyl ethanoate. This is the ester linkage, and it doesn't have any, or even in the rest of the molecule, there's no OH bond. So it doesn't exhibit a sharp peak over here. So this leftover guy has to be my ethyl ethanoate. Can I just highlight one thing right now? Is that this is my, towards the right of this line I'm drawing on the 3 graphs, is my fingerprint region. All of this information, even though as complicated as it looks, is more or less useless to me. Most of my information lies on the left-hand side. Especially these sharp, broad peaks tell me what I need to know. Even before I read the question, I knew this was an acid, I knew this was an alcohol, I knew this was neither an acid, neither an alcohol. Let's try doing more questions. Which of these is butanediol as opposed to butanone? Now, butanediol again will have that characteristic OH and OH lobe in the spectrum, right? But butanone will only have a COO spectrum, and butanone won't really have that CO double bond spectrum. So if we take a look on the right hand side, I find my characteristic lobe dip or peak for the OH bond. That has to be my alcohol. And on the left hand side, I see no such peak, but I do see a small, like a thin, sharp peak for a carbon-oxygen double bond. So this has to be my butanone. And the other one is butan 2-ol. Now I can't figure out if it's butan 2-ol or butan 1-ol, but I know I have to pick between butanone and butan 2-ol. So the questions given to you will be pretty straightforward. You'll know a lot about the molecule itself. You'll just have to differentiate between a few, or it's a very easy. It looks very confusing because of the graphs, but it's a pretty straightforward question every time. Let's do more questions. Before even reading this question, I see my acid, I see my alcohol, I see my not acid, and not alcohol. So it could be an ester, it could be a ketone, not really sure. But let's try reading the question this time. Let's see, which of one of the following, which one of the infrared spectra is that of ethanal? Okay, give 3 reasons. Okay, so this is an OH for an acid. This is an OH for an alcohol. I'm mixing up my brackets. And this is, well, not really anything. So, but I do see my characteristic dip for, I do see it here as well, for the carbon-oxygen double bond, right? So ethanol doesn't really have an OH group, so this isn't it, this isn't it, this is it. C is my ethanol. Now, as far as reasons go, I could say graph A has a broad peak, sharp broad peak from 250 to 350, not 250, 2500 to 3500. And that's characteristic of an acid group. So it can be an ethanol, can be my ethanol, sorry, not ethanol. Whereas same peak, characteristic of an alcohol. So this can be my ethanol. And over here, it doesn't have a peak, but it does have my carbon-oxygen double bond peak. So very likely amongst the 3, this is my ethanol. Those are 3 points. Now, it's really bad advice to start a question without reading about it, but alcohol. I see my alcohol, right? Now let's try reading the question. Okay, compound V gives a silver mirror when it's worn with tolerance reagent. That tells me V is a carbonyl. That's a horrible N. Carbonyl compound, and can be converted to compound W by reagent X. W is this guy. It gets converted into an alcohol. W is an alcohol. Use the spectra below to identify the functional groups present in V and W. Suggest the identity of reagent X. Well, I think it's this graph, the spectra, is confirming that V is a carbonyl because I don't see any alcohol dip, I don't see any acid dip, but I do see a carbon-oxygen double bond dip. So this is carbon-oxygen double bond, and over here it oxidizes and that dip goes away, right? So because it's C3H6, so very likely what's happening is a ketone is being reduced into a secondary alcohol. And the reagent is any reducing agent. You could have H2 with nickel catalyst or lithium, aluminum hydride in ether, in dry ether. That's it for IR spectroscopy. I hope you guys enjoyed this, and good luck for your exams.